Hello viewers on YouTube. In this video tutorial, we are going to consider how the compound angle formula is formed. These formula are one of the formula in trigonometry that contribute a lot in trigonometry entirely as a branch of mathematics. They have a lot of impact in different aspects of trigonometry. By the end of this video, you would be able to understand where these formulas are originated from. So how can we show that? Let's begin by considering a coordinate plane. You already know what a coordinate plane is as a two-dimensional and plane. Alright, we know that all the way upward is our y-axis and all the way to the right or to the left is our x-axis. When it goes to the left, it's negative. Perfect. So now let's assume, or let's take for instance, a rectangle is situated on this plane so that it makes a certain angle with the horizontal. Alright? So we want to situate this rectangle in such a way that it has to make an angle with this horizontal axis x. And how can we do that? So let's just consider this kind of shape. So these rectangles like these, it still makes sense. I hope that's not that tiny. Okay, then you do it again. Okay. Alright. These make sense. Okay. Perfect. It's not a parallelogram, it's a rectangle. Okay. At least this is still well manageable. Perfect. The main thing is just to grab what we are trying to make use of this rectangle for, and not just the diagram. Okay. So now let's consider a diagonal. A diagonal is a line. It has to be a straight line drawn from one vertex of the shape to the other vertex. And this other vertex must be the opposite vertex. So let's consider a diagonal of this rectangle. And let's assume the diagonal is just of 1 unit. So this is the diagonal of the rectangle. So we assume it is 1 unit. Perfect. Now I can clearly see that the diagonal, basically what it does for these regular shapes, square, rectangles, and other, it split them into two equal parts. Okay. Now it makes an angle with the breadth of the rectangle, and let that angle, let it be angle A. Now you can clearly see that the rectangle initially at the beginning, it makes an angle with the horizontal. Let that angle be angle B. Are we following? Perfect. We haven't done anything yet. We are still representing. Okay. So now let's label this rectangle. So let's say it's a rectangle K, L, M, N. Now before we move forward, we have to introduce some other sides. So basically, what I want to do now is that I want to extend this point L all the way to the horizontal axis X. I'm going to do the same thing to point M. I'm also going to extend it all the way to horizontal axis X. And the point at which this extension meets this x-axis, I have to do this as well, so that we can be able to identify it. So let me extend this first. Okay, perfect. Okay, so extending this point L all the way downward, we have to meet the x-axis at P. Okay, and extending point M all the way downward, we also have it to meet the x-axis at Q. Perfect. Now, one more extension. Let's join point M. Let's extend it to this line LP. Now, the point at which this extension meets this LP, we must label it as well so that it can be identifiable. So extending this point M to LP, we have this. So let's call that point O. Perfect. Okay, this is enough for us to show out what we actually want to show that. Perfect. Now, what do you observe? First and foremost, you can clearly see that in that process, we were able to form different shapes. This is NNP, the right angle triangle to say. At the same time, this is NMQ, another right angle to say. In fact, we have POMQ, a rectangle indeed. And lastly, we have LOM, which is also a right angle triangle. Okay. Am I communicating? Incredible. Now, basically, we want to find this angle. Before we begin any of that, I would like to find this angle. Alright? So that won't be complicated along the process. How can we determine this angle with all these information we have on ground? Well, let's begin from here. Remember, at this point, let's also deliver this point here. You can see we have two lines to connect themselves. So let me call that point, let's say S. Okay, point S. Now, at this point S, you can see that NSP is also a right angle triangle, which makes sense. It's a right angle triangle, which means 90 minus angle B must gives us this angle. So what I would do is that I'm going to insert 90 minus angle B as an angle. However, in geometry, we learned what we call a vertically opposite angle. This is an angle whereby when we have two straight lines to connect themselves, then that postulate says that whatever angle that this portion is, it will be the same as this. However, it's being showed out, and to show it out, if this is an obtuse, let's say this is 120 for instance, you can find this one using angle on a straight line. Upon getting this, you can see that this is also a straight line. Then it's just as if you are repeating the process, because 180 minus 20, 120, whatever it gives you, by the time you subtract it from 180, you got 120 back. So instead, a general postulate is formed, which is vertically opposite angle. So this implies that this angle would also be 90 minus B. However, you don't really find this portion. And after finding the portion, find this one as well using angle on the straight line. So regardless, you still end up having the same result. So therefore, we can tell you that this point here is also 90 minus B. 90 minus B. Am I communicating? Perfect. So now, let's pay attention to LSM or LMS. This is still a triangle, and in fact, it's even a right angle triangle, because you can clearly see that these show the right angle. Then that is the case. You can tell that this angle we are trying to solve for can just be gotten by subtracting this one from this one. And upon doing 90 minus B, we can clearly see that we have 90 minus 90 plus B. And eventually we have got B as this portion. And that's what we need. So this angle is going to be B as well. This is perfect. Yeah. So now, upon getting the angles, we can now proceed on seeing if there's any line that can be expressed in terms of one another. Let's begin with line NQ. We can clearly see that line NQ is equal to what? NP plus PQ. Am I communicating? NP plus PQ gives you line NQ. So that will be NP plus PQ. Give it a side. Okay, you can call it equation 1 if you want. Okay, perfect. Now let's look at line LP. That LP is also equal to LO plus OP. LP is also equal to LO plus OP. So therefore, LP is equal to LO plus OP. Incredible. Are we here? Perfect. Now, remember we said POMQ are rectangle. Is a rectangle, they form a rectangle, which means we can clearly say, and one of the properties of a rectangle is that the opposite sides are the same. It means if it is MQ we have, then OP will also be whatever we have as MQ. And if this OP we have, then MQ must also be the same. And same thing applies to PQ and OM. They are interchangeable. Understand? You can use them in in place of one another because the value must be the same. So keep that in mind as well. So now we can call this equation 2. So now let's jump on to SOHCAHTOA. So upon using SOHCAHTOA, let's start with triangle NLM. That's the triangle formed by the rectangle and its diagonal. Should I bring it out? Let me bring it out for those that might be a little bit confused about how the structure is. So I'm talking about this triangle. Are we here? So where this is N, this is L, and this is M. Remember, the angle it sustained was A. Perfect. And this LN is simply 1 as a diagonal. Okay. Our goal is that we want to find this line length and this length. Are we there? Which correspond to NM and MN. So using SOHCAHTOA to find NM, this is M. What would it be? Using sine. Sine A will be equal to what? NM, the opposite, over the what? Hypotenuse 1, which means NM is simply sine A. That's incredible. So I'm just going to put sine A like this. Perfect. So now, what about this NM, which is this? Let's use the cosine. That will be the best thing to use, the best function to use to say. So